Okay, as you can probably see, I'm Gary Carleton from Intel. I've been working at Intel for really more years than I'd care to admit. Most of the time spent on software performance profiling tools. Today I'm going to talk about something a little bit different that really came about, I guess, almost as a function of fear, I might say. Fear is too strong a word, but at Intel we feel that there are not enough tools, not enough concepts to allow the number of programmers that we would like to develop parallel code. So over the last 10 to 15 years, a lot of our research, Tim Matson's one of the people, but a lot of the research and tools we've developed have been focused on trying to enable essentially parallel programs. So one of the things I'm going to talk about today is actually one of the newest components of this effort. We call this the Intel Advisor. The goal of this tool is to help you start with a serial program that works just fine and parallelize it. The goal is to help you identify which portions of the program would be best to parallelize. If you go ahead and do that, what kind of performance might you expect to see? And then as you do parallelize the program, have you created any parallel errors in the program? So this is really the process. It's, again, a relatively new technology. We're still, how can I put this? We'd still like to get more feedback on whether this seems like it's working. We have a number of customers that have used it and have some success. But I think it's a relatively newer type of technology that we need more data on to really determine it. So the goal of this tool is, again, to allow the programmer to prototype parallelism. The goal is to not require the programmer to actually take a serial program, write parallel code with it, then run it, see if it's broken, see if they get any performance. The idea is to not actually write the code, but make some annotations in the source code, do some simulation relative to performance, and do some runtime checking relative to correctness to enable, I think, the first version of the parallel program to be closer to what is really meant to be. So we see really 4 steps in terms of using this tool to do that. So the first step we call survey target. That's simply running the program and using a profiling technology to identify which portions of the program are consuming the most CPU time. So we'll talk about this. Survey target, just where's the program using the CPU a lot? Maybe we should focus parallelization on that particular part or those particular parts of the program. The second step is for the programmer to go into the sources and annotate them in terms of ideas on where parallelism should be in the program, the scope of them, and what really can be done to parallelize the program. So rather than writing code, the programmer just puts in a couple of some annotations, and then our tool takes over to analyze it further. So once the sources are annotated with parallelism sites and parallelism tasks, the third step, perhaps the most important step, and certainly the most difficult from our perspective, is to then run this serial version of the program that has the annotations in it to determine how much faster is this program really going to be if I parallelize this section of the code. So we call this suitability. This is a case where we're running the serial version of the program with the annotations and producing a report on parallel speedup. The final step that this tool goes through is checking for correctness. As you add parallelism, there's certain probability that you'll be creating data races. So the last step of the tool is, once you've identified the parallel model that you think will work for your program, is our tool then will run the program watching for essentially global memory references across thread boundaries to try to determine whether there are new data races that didn't exist before. So the idea, again, is simply find which parts of the program are consuming CPU time. Programmer goes in, indicates parallel actions to be taken. We run the program to see how much faster it's going to be, and then finally to see whether there's any parallelism issues in the program for correctness. Actually, this tool, in a way, it's not really one tool. This tool uses technologies from the different tools that we've been developing at Intel for the last decade or so. The survey target just uses one of the profiling technologies, sampling technologies we have from one of our other tools. The suitability and correctness sort of borrow technology from the threading tools that we've had for quite some time also. So the idea here is perhaps not all that new. It's the collection of these technologies into one tool that's a little bit different. So what I'd like to do now is essentially go through a description of each of these steps in the process. And then at the end of the presentation, I'm going to just bring up the tool and show you how it works to give you an idea of what it can do. I guess I might mention from the practical side of things. This is a tool that we offer at Intel. Currently, it's on Windows only. It's a new tool. We've just put it out there. We're porting it to Linux, and that'll happen soon. But currently, a Windows-only tool. Okay, so that first step I mentioned is this idea of trying to determine which parts of the program are consuming the most time. So here we have a sample output where we've run the survey target part of the tool. It runs the program to completion, again using a hardware sampling, hardware sampling technology to essentially take snapshots of CPU execution context. But the idea is to identify which portions of the program are consuming the most CPU time. And so what we have is kind of a hierarchical spreadsheet, I guess is the way to put it, of the different functions and loops within the program, who they're called by, and the amount of CPU time each one of them consumed. So the idea is once this data is being presented, the programmer can take a look at these, decide to focus on one or more of these, and then go into more detail in terms of looking at that. And the more detail is, you can double-click on any of these items in the GUI, and it takes you to the source code for that specific point in the program. So this first step, really, I think simply stated, the first step is the goal of which is to take you to the source code for where most of the CPU time is being taken. That's really all this is. I think I'd maybe like to spend just a minute on the technology behind this methodology. At Intel, we've had performance profilers for a number of years, and we tend to focus on an interrupt-based technology for gathering performance data. We've experimented with instrumentation in the past where the profiling tool will insert profiling code either at compile time or in the binary directly, and then use that instrumentation to determine which portions of the program are consuming time. But we've always felt that, at Intel, we felt that that type of instrumentation adds runtime overhead and perhaps changes the way the program behaves. So we've always tended to focus on this technology where we allow the program to run as it normally does, a fully optimized build, release build in the Microsoft terminology, and nothing else special in the operating system or anywhere else. The system's just running as it normally does. But what our tool will do is fire off periodic hardware interrupts, and inside the interrupt service routine, simply save away the execution context that existed when the interrupt was acknowledged. So the idea is to just let everything run as it normally does and just take some snapshots of what's going on, build a database of all these samples, and then analyze the samples in a post-mortem kind of manner and produce these reports. So this is our way of attempting to gather performance data without perturbing the system as much as other technologies might. It's a technology we've had for 17 years at Intel in one way or another. So it's a pretty mature methodology. So once we have the source code for where we think most of the CPU time is spent, we can then go to the next step, which is to annotate the source code. So this tool has a set of built-in macros that we've defined. I don't know that the focus is very good there. At least it's not from up here. But in any event, there's a set of macros that you can ask to be placed in the source code, indicating where there's a parallel task, or if there were locking issues detected, or you know they're going to exist, you can indicate that you will go ahead and put some synchronization in at that point. But the idea at this point is to indicate exactly where the parallelism will be in the sources by using these macros as an indication to our simulator that will run as the next step. So these annotations are defined in a header file that comes with the tool. Simply include that header file in your code and you get the macro definitions. Okay, the third step, once we have the macro calls in the program, is to then run the program with our simulator to see what kind of performance improvement or degradation, as we'll see in my demo, that occurs. So you'll get essentially an overall number that represents the performance improvement. You'll see a breakdown by number of CPU cores. So the goal really of this step is to see if the parallelism that you've done is enough. It gets you enough performance improvement that you're done with the parallelism model, then you simply need to go and actually write the code that implements what you told our tool will be your parallelism model. In addition to just showing an overall raw number, it tends to come up with suggestions on additional things you can do to improve the performance. We'll take a look at this during the demo, but some of the classic things are to not keep recreating tasks in a for loop. Some of the task overhead often occurs. Task chunking is to take more than one iteration of the loop and as a single work entity that you give to a task. A lot of different things that can be done to help improve the performance if it's not good enough when you first run the tool. So once you have the program, once you have the parallelism model producing the performance that you like, the next thing to do is to make sure that the program works. The program will work once you do the actual code. So the next step is the correctness report. And again, what that's going to do is basically look for data races. The idea of this step is to not wait for the data races to happen, but simply detect conditions in which a data race may occur. And the classic example is if two different threads are trying to update the same variable, but there's no synchronization around those accesses to that variable. That would be flagged as a potential data race. So we're trying to stop data races from occurring in the sort of more intermittent mode that they normally do in real code, trying to find them ahead of time and allow you to add synchronization or do something else relative to making the fix. I'm going to be talking more about this technology on Wednesday, where I'll go into detail on a tool that focuses on this one step all by itself, the Intel Inspector. So I'm not going to go into great detail here, but the main takeaway from this stage is simply that the data race doesn't have to actually happen. You don't have to see incorrectness occur for us to detect this. We'll just look and see if there's a shared resource that does not have the same synchronization objects that have been acquired across the two threads or more threads. And then there's a summary at the end that will try to give you all this information on one particular screen, essentially showing you those places that were annotated, the kind of performance gain that you did see, that you might see if you add in all the additional ideas that the tool gave. Any errors that were detected in terms of data races are also indicated here. Okay, I feel like I'm kind of going a little fast here. Any questions at this point before I just use the tool? It's a quiet group.
Quick question.
Yes?
Does this examine if you have a program that's already parallel, you start to work with it, or you have to follow a certain program?
This really is for serial programs. I guess you can have a parallel program that you're adding additional parallelism to. The goal here is to not measure. The goal is not to measure performance of an existing existing parallel program. It's to help you determine how to take serial portions of a program to parallel. We have other tools that do parallel performance measurement, and that's a whole other 2 hours of topics. I have to, I'm just dying to mention one thing. I actually got my degree from this campus a number of years ago. And I actually do remember that the audiences were the quietest that I'd ever seen anywhere else. So somehow I feel at home. I don't know that you're this quiet. Go ahead.
These programmers have to write their code in a certain way to help the advisor analyze it?
Okay, the programmers have to write their code in a certain way for advisor to analyze it. I would say, in general, not. We need C, C++. I think Fortran was mentioned, and actually I raised my hand when we said, were there any Fortran programmers? That was actually used on this campus when I was here. Kind of dates myself. But as long as you're using reasonable language, C or C++, and a compiler, there's a couple of caveats. When you compile the program, you should be generating symbols so that we can attribute execution addresses back to line numbers. A fully optimized release build with symbols is required for our technology to work. And you do not have to use the Intel compiler. You can use GCC or Microsoft or anything that produces reasonable symbols. So I'd say there isn't so much a sensitivity of the language, perhaps, as there are using normal industry standard tools to do the builds. Yes? Interesting question. I did not expect that, but the answer actually is yes. The question, and let me see if I got the question right. Do we have any support for student type of development environment as opposed to a commercial one? Is that the idea? And actually the answer is yes. We have an academic program at Intel. I happen to know the guy that runs the program. And part of his job is to focus specifically on certain universities and to make sure the tools are available at those universities. And I would not hesitate to say this one qualifies as one of the universities. So I don't know if maybe Greg Anderson is already at Intel, is already involved, but maybe you can come up to me afterwards and I can get into more detail. But yeah, we have academic pricing specifically in terms of licensing these products.
Can you tell us that pricing?
I can't. That's why Greg Anderson needs to contact you. I can tell you about, writing code and doing performance data, but I don't know the pricing. Sorry, or I don't know the specifics of the different categories of pricing. Okay, let's see if I can get this done here. Okay, so what I've got here is a little program. It's not actually a little program. I've got a program that it's a file compression program. So it opens the file, and it looks at text files. I guess it doesn't have to be. It looks at all bytes of the file, and the idea is to compress it. So we look for the number of occurrences of each different byte pattern within the file. We use a Huffman encoding technique to build a map of that, and then close the input file, write out the output compressed file, and then at the end we check to make sure that the compressed file, the uncompressed compressed file is the same as the original file. So that's what the program does. It's basically just compresses a file using Huffman encoding. And this is what we're going to do to try to determine, or at least to demonstrate the process of taking a serial program, which is what we have right now. There's no OpenMP, no TBB, No pthreads, no Win32 APIs, nothing, just a serial program. We're going to see what we might do to make this more parallel. So the first thing we want to do is to do that, I forget the term that we call it, but to find the performance hotspots in the program. So we'll bring up, let me talk about this environment here first. So this is Visual Studio 2010, in case you don't really recognize it. The advisor is a plug-in to any of the Visual Studios, or at least 2005, 2008, or 2010. The current offering is a plug-in to Visual Studio. And so its icons just become, just get added into the set of icons for Visual Studio. Again, we're porting it, in the process of porting it to Linux now, but it's not out there yet in a public form. So I'll open the advisor, just click on that icon, and over here we get those 5 steps. We get the 4 steps that I described. The fifth step is really you actually writing the source code that does the parallelism. So the first step is to run the program, find out where the performance bottlenecks are. So I'll click on Update. Runs the program, analyzes the results. And what we have in terms of our program is a set of functions, a set of methods here that consumed, a third and a quarter and a sixth of the CPU time here. So we don't really, in this case, have one spot that is a huge performance bottleneck. That it is, 80% of the CPU time, like we saw in the slides. But I'm going to go ahead and use this as kind of an example of the process. I think parallelizing 34% of the program is probably not going to get us really big numbers, but we'll go ahead and take a look at the process. So I can take this function, double-click on it, and that takes us to the source code for that function. Here's count, with some notes on the amount of CPU time consumed by each executable statement in the program. So it's looking like this for loop here is really where a lot of the CPU time is spent. So I might be able to get some benefit in the whole program by simply parallelizing this little section right here. At least that's the hypothesis that we're going to test. So I'll bring up the source code editor, just double click on that for statement. We're now in the source code editor. I'm going to highlight this for loop as the area of the program that I want to parallelize. Right click on it. Bring up the macros that are defined for Parallel Advisor. And we're going to indicate that this is the site, this block of code is the site that we want the parallel analysis to occur on. In addition, we're going to indicate that this statement right here is where we actually want each task to be created. We want each instantiation or each execution of this statement to be an individual thread or an individual parallel task of its own. And that's pretty much what we're going to try and do. So this is, I'm not saying this is the final answer, but this is the first pass of what we're going to try and see what kind of performance improvement we can get if we focus and isolate our efforts just in these couple of lines of code. Okay, so we found the performance bottleneck, survey the target. We annotated the sources. Checking the suitability is the next step. This is where we'll actually run the serial program with those annotations, and our tool will simulate the parallel execution in the annotation site, and we'll see if we get any performance improvement. So I'll go ahead and click Update. Okay, we have a problem. When you make changes to the source code, it's often good to rebuild the program. This is something I've found throughout the years. So we annotated the sources. Let's actually recompile the program. It's interesting what happens when you stand up in front of 100 people. Okay, so we have an actual build now. Now that we have actual executable code with the annotations, let's go ahead and run the simulation. Okay, so now we're getting to see some performance numbers. And to be honest, they don't look too impressive. Here is 1x, that's the speed of the serial program. And we're basically only getting 1/8 of the CPU. The program's going to take 8 times longer to execute based on what we've done so far. So we might want to look at some of these changes that might occur to make the program run a little faster. So we'll enable task chunking, which means we're not going to have a separate task for each iteration of the loop. We'll take multiple iterations and pass them off. What else can we do? Reduce task overhead. We're not going to necessarily create as many tasks as frequently as we indicated in the program. Site overhead. And each of these is, if these are perhaps not totally clear as to what they are, you can click on any of them and you get a nice little essay describing what that's about and other information you can go to. So again, the idea here is to indicate what kind of performance improvement you'll get, and we see the real world where things don't necessarily scale exactly linearly, perhaps even in a positive direction in this case. So the goal here was to show you the process, not necessarily produce a really fast program, but to give you this idea of find the parts of the program that are using the most CPU time, throw a few ideas in the source code in terms of annotating the sources as to how the parallel code will be written, and then run the program, run the simulation of that parallel code, and see roughly what kind of approximate performance improvements you'll get. Okay, given the time, I think I'm going to not actually go into the correctness phase. Again, I've got a talk Wednesday that talks in more detail about how we look for data races, what the user interface looks like when we find them, what the technology is, that type of thing. But the next step would be to look for any correctness issues. And actually, if we think about it even briefly, I believe STR is not thread safe, so we're going to have synchronization issues. But again, that's another discussion for another day. Okay. What else can I say here? In terms of calculating the overhead, you can indicate different models of threading. And we'll sort of point our calculation at the amount of overhead that we feel commonly occurs in the APIs for that particular model. I guess that's pretty much it for the demo. So again, this Parallel Advisor 2001, it's actually a tool. It's a product that we sell. There is academic pricing available, but it's also sold commercially. It can be purchased as either an individual product or as part of a suite of tools. We have a suite of tools called Parallel Studio that has a performance analyzer, which is what you would use to, someone asked about measuring parallel performance, right? Yeah, so there's a performance analyzer in the suite that does that. We also have a correctness tool that looks for threading errors. We have a memory checker, looks for memory issues, memory errors across thread boundaries. We also, kind of a side topic, but we felt that many of the memory checkers out there are really more focused at single thread of execution kinds of data checking. So we came up with one that we felt was more scalable across multiple processors. across multiple threads. So there's that. And there's the compiler. We offer a compiler where we focus a lot of energy on optimization techniques and different ideas for how to make code run as fast as possible. Our compilers are, on the Windows side, our compilers actually plug into Visual Studio. It's not like we're competing. We're just an additional tool that one can use. On the Linux side, we're compatible with GCC. Same binary formats, same source formats, same keywords in the commands, same pragmas. So that's in the tool suite, Parallel Studio. But again, Parallel Advisor is available by itself. Okay, so we need some questions here. Actually, anything on any of the tools. I work in the tool division and have for a number of years. Yes?
Linux version, would that be like a plugin for Eclipse?
It's an interesting question. It's actually a controversial question. We've done Linux tools in the past, and when we had a GUI, we used Eclipse as the GUI. And we have a number of customers, I don't know how to say it nicely, that are very security sensitive. And Eclipse seems to have made more demands on the network in ways that certain system administrators at the national labs didn't like. So it's likely that it will not be on Eclipse, that it will be our own GUI. And in fact, we have other tools, the Parallel Studio compiler, the Performance Analyzer, that do have their own GUI, and they're GUIs that we just did ourselves. So I think it's likely it will not be on Eclipse. Is that something you want to comment on or not? Are we making a mistake? Or if you don't want to say anything, that's fine.
That's fine. I just see a lot of the embedded world, which hasn't done parallel programming, and they're getting introduced big time to at least dual core, maybe quad core.
Yeah, we have a microphone for you if you want to.
So just in the future, where this might play into areas where haven't been parallel programming in the past, which is in the embedded world, and all of a sudden we see multi-core down on mobile devices, and it seems like Eclipse, and maybe I'm wrong, but it seems like Eclipse is moving in a big way in the embedded world.
This is actually an excellent point. We're getting a lot of pressure in the tools group to do more things for the embedded marketplace. So this Performance Analyzer, which is actually the main tool that I work on in my actual job, we are moving it into the embedded environment, where the OSs tend to be a little different and the issues are different. So I think actually in general, software tools for the embedded environment tends to be a significant challenge for our division in particular, because we've sort of more focused at the high end in the past. So I guess I'm not saying anything other than, you have no idea inside of Intel how hard we're trying to work to support the embedded environment more. In fact, I can't resist another little story. About 3 weeks ago, I don't know how I can say this without giving away confidential information. 3 weeks ago, I gave a presentation similar to this. I traveled to Reno and gave a presentation for the embedded market for a company that makes slot machines. I'm not joking. These guys are moving to dual core, actually 4-core systems. And they have the same problems everyone else does. They can't have data races occur. They've got 7 different things they're doing at once in the new machines that they have in the labs. You can't even imagine the applications that we're seeing our processors go into, particularly in the embedded marketplace. And frankly, I think we're a little behind in our tools there. So this is my opinion. I actually took a moment to try out some of their products while I was in there. And I actually took a statistics class here at Berkeley when I was here. Not that helped me lose less money, but I guess I knew why I was losing money. That was the deal. Okay, other questions? Yes.
Did I see a command line interface?
That was the other thing. Good point. Thank you for asking. I can repeat that question.
Pardon?
The question was, is there a command line interface for these tools? And that's what happens a lot of times in the embedded environment, is that many embedded systems don't have a big GUI. You know, there just aren't there isn't the layers of software to do that. So all of the tools that we have a command line interface also, with essentially two versions. One is the data collection part, and the other is the producing a report part. So,
They're using it in Linux, on the report?
yeah. In fact, see, today is Monday. Friday afternoon, I was, again, maybe I can't say too much, but Friday afternoon I was at a Silicon Valley internet company, of which every one of you uses their products. We'll just say that. And they have, you know, all these companies, one of their biggest problems is they have a lot of servers, and they need to make them perform as well as possible. So I sat down with a couple engineers, and we used the performance profiler, but in command line mode, because their servers, you know, you don't need a GUI on a server that's just supplying web pages out to the guy that's using the search engine. So it's very common for, even in the server market, to use the command line only tools, particularly on Linux, it seems. Yes?
So during the Urethane Mum, when you simulate potential performance gain, you can specify you want to reduce code size overhead and or reduce task overhead. But I think it's always a good thing you want to reduce overhead. So I'm just wondering what's the trade-off if you don't reduce overhead?
The trade-off with a lot of these is sort of diminishing returns. You know, if you get to the point in the real world, not that this isn't the real world, I'm sure you have these problems too, but you've got to ship the product at some point, and you don't have unlimited time to do that. So there comes a point where you have to decide, is it worth my time to continue down this path and continue improving performance? Or is it time that I just got to, you know, submit the product to validation and we're done? So I think that's almost more of a personal and a project decision in terms of at what point it's not worth doing more things to the program.
I see. So that means the engineering effort, how much it will
Yes. Yeah, and that's, you know, this presentation is just way too short to really talk about the project aspects. But the goal of this is not to squeeze every last clock cycle out of the program. We're trying to make you more efficient in the fixed amount of time you have to develop a program. That's all we're trying to do. So, you know, if these tools help you make progress faster, you know, my job is done. That's it. Are we out of time now, or?
We still have 3 minutes, and
Okay.
after this, we have a 30-minute break. So.
Even better. Okay, so we have 30 minutes off. We can have another question. Yes?
Do you ever find extends to Fortran?
That's a good question. We support Fortran with a couple of the products. The performance analysis tool does support Fortran, because again, we're not so focused on the language when we're measuring performance. But this tool is pretty much still a C++ tool. Actually, I don't typically see a whole lot of Fortran, and I did not expect to come to this campus and hear the word Fortran, to be honest. Is Fortran occurring here? Or?
A lot of scientific applications.
Yeah, okay, good point. Yeah, that's where we see it, a lot of scientific applications. So Fortran is still out there. Okay. I guess that's it. So we have a
question right here, actually.
Okay.
I just want to ask if you plan to make this product to suggest some of the GPU parallel, or you only want to support it for the CPU parallel too?
Oh, can we look at more than just CPU problems? Is that the question?
Yeah.
Okay.
I want to ask if you will make this product to support the GPU parallelism. GPU.
CPU?
Yeah.
GPU, okay. It doesn't today. That's all I'm going to say. Well, I guess I could say more than that. You know, obviously, we're working on that, but I can't give you any schedules, and all I can say is we don't have that today. Okay, so we have a 30-minute break, and then we'll come back for the next presentation. And thank you.